Hi, I'm SeungJeh in IIIXR Lab. Today I'm talking about the structured 3D latents for scalable and versatile 3D generation called TRELLIS. The primary challenge in current 3D generation research is the lack of a unified representation that can efficiently handle diverse input conditions and support various 3D output formats. TRELLIS addresses this issue by proposing a novel representation called SLAT, which stands for Structured Latent. The workflow starts with an input condition, which can be either a text prompt or a single 2D image. The core of this framework is the SLAT representation. Unlike previous methods that generate specific 3D formats directly, SLAT uses a sparse 3D grid integrated with dense multi-view features. This structural design allows the model to encode explicit geometric structures and detailed appearance simultaneously. To process this, TRELLIS utilizes rectified flow transformers as its generation backbone. The transformer architectures are specially adapted to handle the spatial configuration of SLAT. By training with up to 2 billion parameters on a dataset of 500,000 3D assets, the model robustly maps the 2D or text input into the structured 3D latent space. Finally, the generated SLAT is completely decoupled from the final output format. Through specific decoders, a single SLAT can be transformed into neural radiance fields, 3D Gaussian splatting, or 3D meshes, depending on the downstream requirement. In short, Trellis establishes a unified scalable pipeline that standardizes the 3D generation process across different rendering formats. Thank you.
Today, I will introduce the paper planning to explore via self-supervised world models published at ICML 2020. The main idea of this paper is to learn a global world model without viewers and then use that model to quickly adapt to different downstream tasks. Traditional reinforcement learning is usually task specific. An agent learns a policy using a particular reward signal, and when a new task appears, it must interact with the environment again to collect new data. This paper proposes a different approach. The agent should first explore the environment without viewers, learn a task agnostic world model, and then reuse that model for many tasks with zero shot or few shot adaptation. Another key issue the paper addresses is inefficient exploration. Many curiosity based methods measure novelty after visiting a state, which means the exploration signal is retrospective. Instead, this paper proposes to predict future novelty using a world model and plan actions that lead to informative states. The method uses a latent dynamics world model similar to Planet or Dreamer. Observations are encoded into a latent state, and future trajectories are imagined in this latent space. To guide exploration, the paper estimates epistemic uncertainty, which represents uncertainty due to a lack of knowledge. This is approximated using an ensemble of predictive models. If the ensemble predictions disagree, it means the model is uncertain about that transition. Therefore, the agent plans actions that lead to stage with high model disagreement, which correspond to high expected information gain. An important advantage of this approach is that exploration and adaptation share the same world model. The model learned during self-supervised exploration can later be used to learn task policies without additional environmental interaction, enabling zero-shot reinforcement learning from raw pixels. The results show that this method achieves strong zero-shot and few-shot performance and learns a more general and transferable world model than task-specific approaches. In summary, this paper shows that planning toward expected future novelty in a world model enables effective self-supervised exploration and leads to a transferable global understanding of environment dynamics.
Hello everyone. Today I'll be briefly introducing the paper Gaussian Explorer 3 Gaussian Splatting for Embodied Exploration and Reasoning. The goal of this paper is to enable embodied agents to answer natural language questions about 3D environments by combining 3D scene representations with vision language reasoning. A major challenge in embodied reasoning is that existing systems rely on fixed viewpoints or stored image snapshots. These approaches often fail when the required information is not visible from the recorded views, making it difficult to reason about occlusion or spatial relationships. To address this limitation, the authors propose Gaussian Explorer, which integrates 3D Gaussian splatting with vision language models. The key idea is to treat the 3D Gaussian scene as a semantic memory and dynamically render informative viewpoints to help answer the question. The system works in three main steps. First, the scene is reconstructed as semantic 3D Gaussians, where each Gaussians contain both geometric information and semantic feature extracted from images. Second, given a user question, the system extracts relevant evidence categories, searching the 3D Gaussians that match these concepts, and selects initial camera viewpoints where the relevant objects are most visible. Third, the system performs novel view adjustment. Using the rendered capability of 3D Gaussian splatting, it generates nearby candidate viewpoints and a VLM evaluates them to choose the view that best reveals the information needed to answer the question. This allows the agent to actively explore the 3D scene rather than relying on the pre-recorded images. In experiments on the OpenEQA embodied question answering benchmark, Gaussian Explorer outperforms previous memory-based approaches such as 3D MEM while using a similar number of frames for reasoning. It also improves performance on 3D referring segmentation, showing stronger ability to localize objects described by complex language queries. In summary, this paper demonstrates that combining 3D Gaussian scene representations with VLM-guided viewpoint exploration enables more efficient embodied reasoning in 3D environments.
Hello, I'm SooBin. Today I will be presenting the paper TeamHOI Learning a Unified Policy for Cooperative Human-Object Interaction with any team size, which has been accepted to CBPR 2026. This paper proposed TeamHOI, a framework for running cooperative human-object interaction with multiple humanoid agents using a single policy that works for different team sizes. Recent progress in physics-based character controller has enabled realistic humanoid behavior such as walking, reaching, and manipulating objects. However, most existing approaches focus on single-agent human-object interaction or assume a fixed number of agents. In many real scenarios, such as carrying a table or moving large furniture, multiple people must cooperate. Learning such behavior is challenging because coordination strategy depends on the number of participants and their relative positions. Conventional policies typically use fixed size inputs, meaning a separate model must be trained for each team size, which limits scalability and generalization. To address this problem, the authors introduced a transformer-based multi-agent policy that represents other agents as teammate tokens. Each token encodes the relative state of another agent, such as position, orientation, and velocity with respect to the observing agent and shared object. Because the policy processes these tokens using attention, it can naturally handle a variable number of teammates. During training, environments with different team sizes are sampled, allowing a single network to generalize to multiple cooperative settings. The paper also introduced masked AMP to stabilize motion learning. Transitional AMP enforces similarity between generated motion and a reference motion dataset, but this can restrict the agent when interacting with objects, since hand and arm configuration must adapt to the task. Masked AMP removes object interaction body parts, such as the hands and forearms, from the motion prior discriminator, allowing those joints to be optimized by task reward while maintaining natural locomotion for the rest of the body. Finally, the authors designed a formulation reward that encourages agents to arrange themselves in stable configuration around the objects. The reward promotes evenly distributed position around the object and coverage of its principal axis, helping agents automatically run cooperative formulation for lifting and transporting objects. In this video, we can see that in the previous method, 8 agents failed to move the table like this, whereas TeamHOI successfully completed the task. Yeah, thank you.
Hello, I will briefly introduce contextual neural dynamics. The main question of this paper is, why is context-rich modeling hard? In manipulation, context dynamics are non-smooth and discontinuous. Because of that, even small errors in friction, geometry, compliance, or timing can lead to very different motions. This makes sim-to-real transfer especially difficult. This also explains the limitation of prior approaches. Simply tuning simulator parameters is often not enough because real context dynamics are much more complex and state-dependent. If you look at the top right figure, it shows the real-world setup. The robot interacts with objects using tactile sensing together with object observations. The key point is that this work does not treat context as a side signal. It uses context as an important part of the dynamics model. The bottom right figure shows the overall framework. First, the authors train a base neural dynamics model with a large amount of simulation data. Then they fine-tune it with a small amount of real-world interaction data. So the simulator is kept as a base prior and the model learns context-aware neural dynamics on top of it. Overall, this paper shows that explicitly modeling context can improve state prediction and help sim-to-real policy evaluation and refinement in context-rich manipulation.
Hello, I'm JuYeong, an integrated student. Today, I'm going to present Navigation World Model, the best paper at CVPR 2025. This slide introduces the Navigation World Model, or NWM, for visual navigation. A key limitation of existing visual navigation policies is that once trained, they are often difficult to adapt to new constraints or planning objectives. To address this, the paper proposes NWM, which predict future observations instead of directly outputting actions. This allows the agent to imagine possible future trajectories and use them for planning. Now, let me briefly explain how the model works. MWM encodes the current image observation X into a VAE latent representation S and predicts the next latent based on past latents and actions. The action space includes planar motion, yaw rotation, and a time shift, which indicates how far forward and backward in time to look. The model is built on CDIT, or Conditional Diffusion Transformer. In this architecture, the target frame uses self-attention, while past frames are incorporated through cross-attention, allowing the computation to scale linearly with context length. For evaluation, the method is tested on several open navigation datasets, including scanned Tartan Drive, Recon, and Huron, as well as Ego4D and Go-Stanford for unseen environment evaluation. Overall, the key idea is that MWM supports navigation by predicting and evaluating possible futures rather than relying only on a fixed navigation push. To give an intuitive example, in this video, the word model simulates actions P1, P2, and P3 from the input images and selects the action that is closest to the goal. Thank you for listening.
Hello everyone, my name is SeungJeh. Today I will present a paper titled AutoVLA. Now I will introduce the main idea of this paper. This slide shows the main idea of VLA. First, on the top left, the paper explains the limits of previous methods. There are two main problems: inefficient listening and inefficient output. In simple driving scenes, some models still use long listening, which makes inference slow. Also, some methods generate outputs that are hard to use in real driving. To solve these problems, the paper proposed two key ideas, shown in the top middle and top right. The first idea is thinking mode adaptation. This means the model does not use the same amount of listening for every scene. Instead, it changes its reasoning style based on the situation. The second idea is physical action tokens. Instead of directly generating a continuous trajectory, the model changes vehicle motion into discrete action tokens. Then it generates these tokens one by one to build a final trajectory. This helps the model produce actions that are more realistic and easier to use for driving. The bottom part shows your thinking mode adaptation, which is the core idea of this paper. AutoVLA has two modes. The first is fast thinking. In simple scenes, the model skips long listening and predicts the action directly. This makes inference faster and more efficient. The second is slow thinking. In complex scenes, the model uses step-by-step listening before making the final decision. It looks at the scene, finds important objects, understands the situation, and then chooses the driving action. The example in the bottom middle shows a construction scene. The model sees the worker and right lane and then decides that changing to the left lane is best action. The example on the bottom right shows the same idea. In easy scenes, the model gives a short and direct answer. In hard scenes, it uses longer listening before planning. In summary, this paper tries to solve inefficient listening and inefficient output by using thinking mode adaptation and physical action tokens. With these ideas, AutoVLA can use the right amount of listening and generate more practical driving actions. Thank you.
Today I will be presenting a paper titled WorldCoder, a model-based LLM agent building world model by writing code and interacting with the environment. This is a NeurIPS 2024 paper that explores how an LLM agent can run an executable world model by writing and refining code through interaction with an environment. I choose this paper because it offers a comparing perspective on using LLM not just as planner, but a system that explicitly constructs world model for decision making. This slide summarizes the core idea of WorldCoder, a model-based LLM agent that runs to act by writing code for the world. The main goal of WorldCoder is to run an executable world model, meaning a program that predicts how the environment changes after an action. Instead of relying on the language model to decide every single move online, it first built a simulator of the environment and then planned with the simulator. This matters because code-based world models are interpretable, editable, and reusable. Once the model is written as Python code, we can inspect it, revise it when it fails, and transfer parts of it across tasks. It also reduces the need to query the LLM at every step, which can make decision-making more efficient. What WorldCoder does is fairly simple but powerful. It collects interaction data, then uses an LLM to synthesize transition and reward function as executable code. After that, a planner uses the learned model to search for good action, while optimistic estimates encourage exploration in sparse reward setting. In terms of training, the agent begins with random exploration and stores transition in a replay buffer, which is just the memory of past interaction. Then the LLM proposed code check it against observed failure and iteratively repair the program. With the improved model, the agent performed planning using methods like value iteration or MCTS, which stands for Monte Carlo tree search. The key result is that WorldCoder learned useful world model with relatively little experience and outperformed strong language agent baseline on challenging tasks. More importantly, it goes beyond imitation. It does not merely mimic action pattern, but construct an explicit reusable model of environment dynamics and improve it through counterexample.
Hello, my name is SeungRae. Today, I'll introduce the paper titled AI Can Learn Scientific Taste. The core question of this work is simple. Beyond executing research tasks, can an AI learn scientific taste, meaning the ability to judge which ideas are more promising and to propose ideas with higher potential impact? The authors argue that this capability is missing in most current AI scientist systems, and they frame it as a preference modeling and align problem. The method has 3 stages, shown on the left side of the slide. First, they collect community feedback. Their key idea is to use citations as large-scale supervision. To reduce bias, they match 2 papers from the same field and year and treat the most cited one as the preferred item. This produces SCI Judge Bench, a dataset of about 700,000 field and time-matched paper pairs. Second, they train scientific judge model. Given a pair of papers represented by little and abstract, the model predicts which one has higher potential impact. It is trained with GRPO, where the reward is simply whether its preference predictions matches the citation-based label. So the judge learns to approximate the scientific community's long-term preference signal. Third, they train scientific thinker. Here the output is a seed paper, and the model generates candidate follow-up ideas. Since there is no direct ground truth for ideation, the others use scientific judge as a reward model and compare generated ideas pairwise. The win rate from these comparisons becomes the training signal for the thinker model. Now the results. In the bottom and right panels, the trained scientific judge outperforms strong baselines and proprietary models such as GPT 5.2 Thinking and Gemini 3 Pro on their benchmark. The paper also reports generalization to future year test sets, unseen fields, and peer review preference. For ideation, scientific thinker consistently beats its untrained base policy. On the slide, the 30 billion model reaches 81.5 in domain win rate, and the detailed results also show gains out of domain. So the main takeaway is, this paper suggests that scientific judgment and scientific ideation can both be improved by learning from large-scale community feedback. It is an interesting step toward more capable AI scientist systems.
Hello, my name is ByungMin Kim from IIIXR Lab. Today I'll be presenting Struct2D, a perception-guided framework for spatial reasoning in multimodal large language models published at NeurIPS 2025. When we give MLLMs raw video frames for spatial reasoning, they face two fundamental problems. First, incomplete perception. Video frames are sparsely sampled from limited viewpoints, so critical objects can be missed entirely due to occlusion or camera angle. Second, lack of global context. Egocentric frames are fragmented, so the model never gets a holistic view of the scene. It can't tell whether the lamp is closer to the couch or the bookshelf if they never co-occur in the same frame. Previous approach tried to solve this by feeding 3D point clouds directly into LLMs, but that requires specialized architectures, additional training, and expensive infrastructure, which limits scalability and real-world applicability. Struct2D takes a fundamentally different approach. Instead of forcing the model to interpret raw 3D data, it transforms 3D perception outputs into structured 2D inputs that MLLMs already understand well. Starting from an RGBD video, a perception model reconstructs a 3D point cloud and performs object detection. Then, this 3D information is projected down into a bird's eye view image with object marks drawn on it. Importantly, these marks are filtered so that only objects relevant to the current question are shown, reducing visual clutter and helping the model focus. Along with the BEV image, the model receives object-centric metadata as text, things like object categories and their 3D coordinates, and when appearance cues are needed, such as object color or size, selected egocentric keyframes are provided using depth-aware frame selection. For relative direction tasks, the BEV image is rotated to align with the agent's facing direction, making spatial reasoning more intuitive. And a structured guide prompt walks the model through geometric reasoning steps, like drawing reference lines to determine whether something is front left versus back right. The results strongly support this approach. In zero-shot evaluation, GPT-03 with just a single BEV image and metadata significantly outperforms the multi-frame baseline across spatial reasoning tasks, while using far fewer input images and costing a fraction of our API budget. The ablation study confirmed that every component matters. Metadata grounds the model in precise spatial context. Filtered marks reduce ambiguity. Rotation alignment and the guide prompt are each helpful on their own, but combining them gives the best performance in direction tasks. What I find most compelling about this work is the core insight. The bottleneck in VLM spatial reasoning is not perceptual, it's representational. VLMs struggle with raw depths and point clouds, but they are surprisingly strong at reading structured 2D layouts, symbols, relative position, and text metadata. Struct2D exploits exactly this gap. To summarize, Struct2D demonstrates that with well-designed structured 2D prompting, MLLMs can perform strong 3D spatial reasoning, no explicit 3D representations needed. Thank you for listening.
Hello, I'm Haneul Kim from IIIXR Lab, and today I'll introduce MoE-Loco, mixture of experts for multitask locomotion, published at IIIX 2025. So this paper proposed a method for learning multiple types of terrains and locomotion styles within a single policy in an R-based robotic environment. So robots operating in diverse terrains and locomotion modes requires a unified policy. But existing multitask RM muscles suffer from gradient conflicts between tasks, which degrades learning performance. Training a single policy across heterogeneous terrains and gates also leads to instability and limited generalization. So, this method adopts a mixture of experts architectures, so that multiple experts within a single policy can naturally specialize in different local strategies and terrain. In the architecture on the left, it represents exteroceptive information such as friction-related environmental properties, and IT represents richer privileged information such as link-wise contact force. So these two types of features are available in simulation, but are difficult to obtain directly in real-world robotic systems. In contrast, PT proprioceptions consist of internal sensor measurements that are available on real robots, such as projected gravity and joint position. So, there are three observation features are combined with a one-hot vector CT, which specifies the locomotion modes, and the resulting vector is fed into the LSTM. So the output is then processed by the actor MoE and critic MoE, which learn the policy that predicts appropriate actions and state values across diverse terrains and locomotion style. So the gating network computes weights that determine which expert outputs should be selected or combined based on the current input state. Through this mechanism, different experts become specialized for different terrains or locomotion strategies. And the estimator on the far left is a module designed to facilitate sim-to-real transform. So it takes proprioceptive observation that are available on real robots as input and is trained to estimate the privileged information that are available only in simulation. So, on the right side, this figure visualizes the output of the gating network using TSNE. Each point represents the features produced by the gating network for given states, and the colors indicates different combination of terrain types and locomotion modes. An important observation is that different tasks form clearly separated clusters. Overall, this work shows that a MoE-based policy can lead diverse locomotion behaviors across terrains within a single unified policy while remaining transferable to real robots.